Today I have a super quick explanation of rusting and how we can prevent it. Before we start, I think we should all take a moment just to appreciate how amazing my diagram is. Excellent, let's go. So rusting. Rusting can be summarised by the following equation. We have got iron reacting with oxygen in the presence of water to make essentially hydrated iron oxide, so Fe2O3.XH2O. And the X there indicates that the number of water molecules associated essentially with each unit of iron oxide is variable. However, the actual process is a little bit more complex, and we're going to dive into the electrochemistry here. It happens via a series of half reactions. They take place both in the iron and in the water droplet. So let's start right here, right in the centre of our iron, where the oxygen concentration in the water is very, very low because it's the centre of the water droplet. So if we can appreciate that oxygen from the air is going to dissolve in water, and the concentrations of oxygen are going to be highest around the edges of the water droplet. So the first thing that we're going to see happening is iron being oxidized to Fe2 plus ions, and the standard electrode potential for that half reaction is minus 0.44 volts. So this is step one. These iron ions are then going to move into solution, into the water droplet. And as we can see there, we've got a nice dip in our iron as the iron itself is moved into Fe2 plus. These electrons are going to be used to reduce oxygen and water to form hydroxide ions. So let's have a look at that half equation. So we've got oxygen plus water plus electrons going to form hydroxide ions. And the electrode potential for that is plus 0.40 volts. So we can see with these two half cells that the iron half cell is going to be the oxidation half cell. It's got the less positive electrode potential, and the oxygen water half cell is going to be the cathode, the reduction half cell. So we need the electrons from our first half cell in order to reduce oxygen and water to hydroxide ions. These electrons are going to be flowing through the metal to the place where we have a high concentration of oxygen in our water, so the edges of the droplet, where the second half reaction is going to take place. So at this point I have Fe2 plus ions in solution in my water droplet, and I'm also going to have hydroxide ions. And Fe2 plus and OH minus will react together, precipitate out to form iron 2 hydroxide. And that's a greenish precipitate. The Fe2 plus in this compound is further oxidized by the oxygen in the water droplet to form Fe3 plus, and they also react with the hydroxide ions and water to make our finished product rust. So we can see that essentially we have got a couple of reactions happening. We label that one 3. I've got a couple of reactions happening: formation of iron 2 hydroxide, oxidation of Fe2 plus to Fe3 plus, and then the formation of our rust compound, the hydrated iron 3 oxide, and then that forms on the surface of the iron. Now, unlike many metal oxides, rust doesn't adhere tightly to the surface. It doesn't form its own protective layer, unlike zinc, for example, or aluminium forming aluminium oxide. So the rusting process can continue to happen unimpeded underneath the rust. If you are following the OCRB Salters Chemistry A-level syllabus, I'll give you the heads up. You'll be expected to know those two half equations, so you need to commit those to memory. How do we prevent iron from rusting? The simplest way is to paint the surface. And that way we have a protective barrier between the water and the oxygen and the iron. We could use oil or grease as well. This method, although very simple, is only going to work as long as the barrier is in place. Method number 2, galvanizing. So this is where we take our iron object and we coat it in a thin layer of zinc. Zinc in the presence of oxygen forms zinc oxide. And zinc oxide is an impermeable layer that prevents further corrosion from happening, unlike rust. If the zinc layer is chipped in some way, then a series of reactions are going to happen. First of all, iron would be oxidized to Fe2+ by oxygen and water. However, if we have a look at the standard electrode potential data for iron and zinc, we can see that the zinc half cell has a more negative, less positive standard electrode potential. So any Fe2+ that are formed would be reduced back to Fe, because in the presence of zinc, zinc would be the oxidation half cell and iron would be the reduction half cell. So that's method number 2. Method number 3 is using a sacrificial anode. And this is where we take our iron object and we link it with a wire to a metal, a block of a metal, that is more easily oxidized. Magnesium is a common example. Why would this work? Well, again, if we go back to our standard electrode potential data, we can see that the magnesium half cell has a considerably less positive standard electrode potential compared with iron. It's sacrificial because as the magnesium corrodes away, we're going to need to replace it from time to time. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.